We're just starting on the type 3, which I tried to make you do on the worksheet yesterday, but I haven't taught you that yet, so I told you to cross it off.
This is still in section 1, right?
What?
Still in section 1?
No, this is section 2.
Oh, this is section 2,
Covalent compounds.
Is that more, do hydrates go under that then? Or
What?
Do hydrates go under that, or do they go in section?
No, hydrates are under section 1.
Okay, so this is the start of section 2.
This is the start of section 2.
Alright, thank you.
Okay. So in section 1, we are mostly talking about our ionic compounds. And the type 1 and type 2 compounds are going to be ionic because it's a metal and a non-metal. Now with our covalent compounds, we're looking at how two nonmetals can share electrons to form a covalent compound. And these ones are by far the easiest ones to name. So, our essential questions, which are listed on page 168. How do the properties of covalent substances compare with those of ionic substances? How do allotropes of the same element differ on the submicroscopic scale, and how do they differ with regard to the macroscopic properties? And how can a formula of a covalent compound be used to generate a name for the compound? Review of vocabulary. In the last lesson we did anhydrous, which is a compound which all the water has been removed, usually from the heating process. New vocabulary: distillation, molecular element, allotrope, organic compound, inorganic compound, and hydrocarbon. Our main idea is that covalent bonds will hold atoms in a covalent compound together. So that is through the sharing of electrons versus something having a charge on it. So, properties of most ionic and covalent compounds are different enough that their differences can be used to classify and separate them from one another. So an ionic compound has very different properties than that of a covalent compound. And that is because of the electron configurations when ions form, and then when ionic compounds form by giving up or accepting electrons, becoming electrically charged then, versus covalent compounds in which they share those electrons. So very different properties because of the way that they bond. We can use a process of distillation, which there is a picture of a setup of a distillation apparatus on page 169 in your books. But distillation is the method of separating substances in a mixture by the evaporation of a liquid and the subsequent condensation of its vapor. And most covalent compounds are not electrolytes, like ionic compounds are, because they do not easily form ions. However, we are going to see type 3 compounds that form when fluorine, chlorine, bromine, iodine, when they form a compound with another non-metal, by sharing electrons. Okay, so this says they covalent compounds are not electrolytes because they do not easily form ions, even though fluorine, chlorine, bromine, iodine do form ions easily. But it's that they are sharing electrons with another nonmetal. So when they're sharing electrons, they're not going to become an ion. So when we have the sharing of electrons then, okay, a molecule that forms when ions of the same element bond together is called a molecular element. In this case we have oxygen and nitrogen. So we have O2, N2. These are also those diatomic molecules, and I'm pretty sure I had you mark them on your periodic table. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine are all diatomic molecules or a molecular element, meaning two atoms of the same element sharing electrons to become stable. So when we look at these ones, the oxygen has 2 electrons that are unpaired. Well, if they meet up with another oxygen atom that has 2 unpaired electrons, you're going to share those 2 pairs with each other then, forming a double bond here. We have a diatomic molecule or a molecular element. Nitrogen has 3 unpaired electrons in each atom. And so if they share those electrons, then we get 3 shared pairs of electrons, and again get a diatomic molecule. And this is what I was just talking about with the diatomic molecules. So 7 nonmetal elements are found naturally as diatomic elements, diatomic molecules, or molecular elements of 2 identical atoms. So H2, N2, O2, F2, Cl2, Br2, I2. Those are diatomic molecules. Again, you should have had that wrote on your periodic table, but you can write that on there. Like, I don't know, you might just write like across the top, diatomic molecules, and put H2, N2, O2, F2, Cl2, Br2, I2. Because when it comes time, when we get into like chapter 6 and chapter 12, and we're starting to write out chemical reaction equations, and it says hydrogen gas is reacting with blah, blah, blah to form this, okay? It's going to be really important that you know that hydrogen gas is H2. It's not just H. Or if it's nitrogen gas reacting with whatever, it's N2, okay? So those are things that you are going to need to know. So if you write that on your periodic table, then you have that information there for you. Molecules of a single element that differ in crystalline structure or molecular structure. If you go to page 174 and 175, it talks about carbon as an allotrope. Okay. So substances that have the same chemical makeup but are very different because of the way that the atoms are arranged are allotropes. So properties of allotropes are usually different even though they contain the same element. Okay, diamond and coal are really good examples of that because we're all very well aware of what diamond and coal are. What do we know about diamonds? Made up of 100% what? Carbon. Okay, diamonds are made up of 100% carbon. They are the hardest naturally occurring substance in the world. Very valuable. And it's because of their structure that they are so hard. The bonds that hold it together are very, very strong. They're all equal and they're very, very strong. Okay, what do we know about coal? It is also 100% carbon. If you took a hammer to a piece of coal, would you be able to break it?
Yes.
Would you be able to do that with a diamond?
No.
No. Okay. And if they're both 100% carbon, how can you break the coal versus not being able to break the diamond?
Weak structure.
Weak structure. Okay. Who's writing with a pencil right now? Anyone?
Nope.
What's in your pencil?
Wood.
It's not actually lead. It's graphite, which is also made up of carbon. Okay. And you're able to write on your paper with graphite because it's very, very soft and it scratches off as you move it across your paper. Okay? You try to write with a diamond, is that gonna scratch off on your paper? No. Okay? Again, it has to do with the structure of it. So the bonds that hold the graphite together are very, very weak and uneven, so it allows it to break off very easily versus that of diamond that are very strong and equal to each other, makes it a very strong substance. Okay. And there are a lot of other things. Carbon's just the easiest thing to talk about when in terms of allotropes. So we're talking about things that are made up of the same thing but have very different properties to them. Bottom of page 173, figure 20, it talks about white phosphorus and red phosphorus. Okay, they're both made up of phosphorus. But they are just structurally bonded together a little bit different, so it gives them some different properties. So, here, talking about phosphorus. So, phosphorus has 3 common allotropes formed from P4 molecules that are joined in different ways. Each allotrope of phosphorus has a unique structure and set of properties. And you can see 2 of those allotropes of phosphorus there. The carbon allotropes there on page 174, 175, you have graphite, carbon blacks, diamond, and charcoals are all examples of that as well, of different allotropes of the same thing. So chemically made up of the same thing, just very, very different characteristics. Oh, they have fullerenes. If go on to page 176, fullerenes, which it looks kind of like a soccer ball, and linear acetylenic carbon.
What did you just say?
Linear acetylenic carbon. Acetylenic? Probably acetylenic. Produced by using a laser to zap a graphite rod in a glass container filled with argon gas. The allotrope splatters on the glass walls and is then removed. Because they conduct electricity, the carbon filaments may have uses in microelectronics. Interesting. Again, carbon has several important allotropes with different properties. Diamonds are crystals in which the atoms of carbon are held rigidly in a place in a 3-dimensional network. Very strong bonds because they, like I said, they have the same strength regardless of what other carbon atom it is bonded with. Graphite, carbon atoms are held closely together in flat layers that can slide over each other. So because graphite has that ability, they can slide over each other. If you guys have ever done this where you like take some of your pencil lead, your graphite, and like if you color on something and then wipe it and you go like this with it, it's very slick, right? It can be used as a lubricant as well. Used in agriculture a lot as a lubricant so that like seeds don't get stuck in like drills and planters. And then allotropes of oxygen also. O2 is the oxygen that we need in order to breathe. It's what gets distributed to all of the different parts of our body in order for our cells to undergo cellular respiration. But there is also O3, which is ozone. So it consists of 3 oxygen atoms. Is naturally occurring as well, but can be harmful to living things. So you can't swap out the oxygen that we breathe for ozone and be able to continue to live. We specifically need O2 instead of O3. We can classify substances as either being organic or inorganic, and that's a little bit different of a definition for science class than what it is. Like if we start talking about like organic foods and stuff like that, things for consumers to buy that they say this is organic. So that definition and the like biologic, chemical, scientific definition are 2 different things. When we are talking about organic compounds, especially in chemistry, we are talking about compounds that are carbon-based. So compounds that contain carbon, with a few exceptions, are classified as organic compounds, as opposed to like when we're talking about them as consumers, something that is organic, meaning that it is grown naturally, it doesn't have any additives to it, hasn't used pesticides or herbicides or anything like that. So very, very different definitions for organic in science and in as a consumer. And then compounds that don't contain carbon are going to be called inorganic compounds. If inorganic compounds contain only 2 nonmetal elements, they bonded covalently and are referred to as a molecular binary compound. And if you go to college and you're majoring in something that requires you to take lots of chemistry, options for you to take would be organic chemistry is one of them, and sometimes inorganic chemistry. And so you're only, like with organic chemistry, you're only dealing with compounds that have carbon in them, or if you're doing inorganic, you're only dealing with compounds that do not have carbon in them. Well, I don't know if you've met her before, but she's really not that athletic. No offense.
I know.
Yeah, kicking takes athleticism.
I can throw stuff.
I'm not very good.
I can hit a volleyball, but I'm not a good kicker. Last one?
Not quite.
Number
Is
eight,
it
right?
like 5 of them?
You have, including this one, there's 3 that actually have stuff on it that
Okay, cool beans, I can do it.
I told you it's not going to take us that long. Okay, so kind of to wrap up what we've been talking about with type 1 and type 2 compounds and how if we have a formula, we can get to a name of it, or if we have a name of it, we can go to a formula. Okay, these are our type 3 compounds. They are covalent compounds. And as I said, they are the easiest ones to do of type 1, type 2, type 3 because it literally gives you what is present, so nitrogen and oxygen. And then it tells you how many. And then you're going to use the table that is in your book. It's on page, what page was that on? I had the table 5 that was on page 165, but it's also on that piece of paper with all the tables on it. You're going to use those prefixes to tell how many there are. So when we look at table 5 and we see that there's a 2 on there, what's the prefix for 2? Di. And so we're just going to put di, the prefix, onto nitrogen, so we get dinitrogen. And then we have oxygen here. And how many do we have? And what's the prefix for 3? Tri. And so we're still changing the ending from of oxygen to oxide. But we're putting that prefix on there and we get trioxide. So like it literally just tells us everything that we need to know about what elements are present and how many of each of those elements is present. So these are the easiest ones to do because of that. So first thing we're going to do is we are, for the most part, and it does not always happen this way, and I'm sorry, for the most part, when we are looking at the periodic table and we're dealing with 2 elements, so we have nitrogen and oxygen, for example, when we look at them on the periodic table, the one that is farthest to the left is going to be listed first, which is what? Nitrogen or oxygen? Nitrogen. Okay, so that's going to be our first one. Then followed by the second non-metal. We're going to change the ending to IDE still. So might be oxide, fluoride, chloride, bromide, iodide, sulfide, phosphoride, nitride, carbide. Okay, hydride. You are going to have probably a hydride in there, which doesn't make any sense because hydrogen, like you can't get any more left than that. I don't know. Like I said, there are a few exceptions. I know. I don't know. They didn't ask my opinion. I just have to teach it.
You don't create science with you?
No. Okay. And then we have to add the prefix from that table 5 to the name of each element to indicate how many atoms of each element are present. And there is an exception, which I'm going to talk about on the next slide so that you can see the example there. What are you doing? Okay, so looking at this, we have 1 nitrogen and 1 oxygen. So when we look at table 5, okay, we look at our prefixes. What should the name of our compound be? 1 is what? Prefix for 1 is mono. Mono means 1, okay? And so we have 1 nitrogen, 1 oxygen. Okay, why do we not have that here?
No.
But we have it here.
Because the first word doesn't
Because
mean
nitrogen is before oxygen.
Because science is dumb.
Okay?
yeah.
When it is the first element there and there's only 1 of them, we do not need to change the prefix. Okay? If it's 2 or more, we're going to put a prefix on that first one. If it's only 1, we're not going to put a prefix on it. So we should never have a compound that starts with mono. Okay? However, we get to that second one. So we have NO, NO2. We have to have a prefix on those to indicate how many of each we have. Okay, so nitrogen monoxide, okay, that tells us that we have one. We don't have more than that because we don't have a prefix, okay, and then monoxide, mono meaning one, okay, so now we have one oxygen. Something very similar, NO2, okay, so we have one nitrogen, di for the two, so dioxide, okay? But then we have something like N2O, so we would have dinitrogen, we would add di to the beginning of that, because we have more than one, and then monoxide, and then we have dinitrogen pentoxide.
Five?
Yep.
I got that difference.
Yes. So, like I said, like whether we are given the formula, it's very easy for us to come up with the name of it, or if we are given the name, it's very easy for us to come up with the formula. It's the easiest one out of all three types of compounds to do. On page 180, this is table 7, which should also be on your paper. Okay. There are some common names for some acids there. And again, I put it on the table there because I don't expect you to memorize them. I pretty much know them just because I have used them for several years. I don't necessarily expect you guys to memorize them though. But so some scientists will use more common names for certain compounds such as water, ammonia, and sulfuric acid. So those are in table 7 for you, so that you don't have to memorize them. And then we're gonna look at table 8, which has hydrocarbons on there. And again, I am not going to require you to memorize them. That's why they are on a table on that piece of paper for you. So, the name of even the most complex organic compounds is based on the name of a hydrocarbon, which is an organic compound, contains only the elements hydrogen and carbon. And compounds containing noble gases such as helium and neon have never been found. Why do we think that noble gases do not create compounds?
They have 8 valence electrons, so they're stable. They have no reason to combine.
Okay, they're chemically stable because they have the 8 valence electrons. Their outer energy level is already full. They're stable. They don't form compounds in nature. Can they force them to form compounds in a laboratory? Yes, but don't need to. And this is just your hydrocarbons. We don't spend a ton of time on hydrocarbons either. However, when we get into writing chemical reactions, sometimes they will give you one of these hydrocarbons, say it is burning in the presence of oxygen. What are its products? Always CO2 and H2O.
Okay.
You just have to balance it, but yeah. So these are also given a prefix for it, and they are related to how many carbons are in each of these. But I don't expect you to know that. You don't need to memorize that. You have the table there for you.
Still nothing.
Okay.
Nothing.
Any questions? Okay. Gonna give you a worksheet. This is for practice problems 13 and 14 on page 179. It says 1 and 2 here, but 1 is 13 and 2 is 14.